everyone. So I will dive in right away. So today I'm going to present our universal guide for custom fitting implants for continuous and discontinuous skulls. So in primate neurobiology, chronically implanted devices such as head posts are used for head stabilization or chambers to gain access to the brain to study its activity. And such implants are skull mounted and made from hard, durable materials, as we were discussing before already. So they need to be very well fitting because you want to avoid infections and especially tissue growth. So recent approaches actually started to design those implants virtually before even manufacturing and to virtually match them to the skull surface. However, with our guide, we want to introduce a method that even expands this functionality and usability and is at the same time very well suited also for non-cut experts. So our guide is not only suitable for even skull surfaces, but it also is very well usable for skulls with special conditions, like for example, if they have some holes in there. It additionally is like it's already using the so-called virtual bending and virtual cutting approaches, to which I will come later, but we are also introducing the virtual bending approach. And the final design can be used for 3D printing or CNC milling, which allows you to use a variety of materials. So before we dive into the specific steps, I just want to very briefly give you an overview of our technical specifications. So in our guide, actually, we are also explaining how to extract brain and skull models from MRI or CT scans by using 3D Slicer. However, now I want to focus on the implant designing procedure. So the raw designing can be actually done in any CAD software of your choice. So in our guide later, we are actually explaining how to use this by using Fusion, but you can also use any other software that you want to use. And the fitting is then done in Rhinoceros 5. And actually this is also a program, also a CAD program, with which you can also already design the raw implant. And then the manufacturing was done by using either CNC milling or 3D printing, but then again, I will come back to this later. So coming back to the first point I made before, so as you can see here on the left, we have a skull of a monkey from our lab, and his skull contains clearly several holes, and that was due to a prior infection. However, the animal was then completely healthy, and therefore we wanted to implant this animal with a head post for head stabilization and also with a broad expanded chamber for wireless recordings. So details about the wireless recordings itself and especially about the wireless chamber design can be found in the paper of a colleague of mine by Michael Berger et al., who published actually this year. I just mainly and briefly want to focus on the implant itself. So as you can see on the upper part, we were not only able to match the skull surface with our head post, but we could also take this hole actually into consideration while designing, and then, for example, giving an extra protection by covering this hole with an additional leg. And coming back to the lower part, we can see that that we managed to even customize the implant that is quite extended, like it's covering 2/3 of the skull surface itself, and still doing our wireless recordings. So all of the recently published matters make use of what we call, or what we refer to as now, virtual cutting approach, which means that you design your raw implant and then you fit it to your skull surface by subtracting the skull surface from your raw implant. And this method works actually very well as long as there is no need to maintain the constant bottom thickness. However, maintaining this bottom thickness can be sometimes very useful. For example, if you are limited in the screw length and you do not want to insert a very broad range of screw lengths, for example, ranging from 5 to 10 millimeters. So for this, we also introduce on top of it the virtual bending approach. For just to briefly describe because of time reasons. So what we do here is we project the 3D extracted skull surface to a 2D reference surface. And then on this, we design our implant. And then this 2D flat implant is then reprojected into the 3D space, which basically allows you to bend this flat implant around the 3D skull surface. And with this approach, of course, you can also combine your implants and design implants that make use of the virtual bending as well as the virtual cutting. And then in the end, of course, again, the last point that with this, our final file design allows you to either use CNC milling, which is very useful for PEEK, for example, or create implants in PEEK, and also for 3D printing. And here you can, of course, use different type of 3D printing. So for example, we use the 3D laser sintering printers to create our titanium head pose. And we also use the more commonly used fused disposition modeling for PLL or nylon. And so with this, the 5 minutes are over, and I want to summarize that our guide is actually suitable not just for smooth skull surfaces, but it's also very useful for special conditions like having holes in your skull. We are using the virtual cutting method, but on top of it, we are also adding the virtual bending method, which can be quite useful in some specific cases. And in the end, we are able to 3D print or even CNC mill those virtually designed files, which gives it a more flexibility, more broad flexibility in terms of the materials. And most importantly, we are providing actually a step-by-step tutorial, including video tutorial, that is very well suitable also for non-experienced cut users. So in theory, anyone can design it. And with this coming to an end, so it's not submitted yet, but it's very close to submission. However, please don't be hesitant and don't wait for it. Like, I will be very happy to provide the tutorial. And also, if you have any question, just write us an email. Here you can also find the GitHub page. And specifically, if you use the tutorial, we will be happy about any type of feedback that you can give us. And with that, that's it. Thanks.
Thank you so much, Zurna. While we wait for some questions from the audience, I have some questions of my own. So I come from the land of mouse skulls, so I'm less familiar with primate skulls. So kind of a naive question, how much variation do you have between, let's say, an average primate skull from primate to primate? This obviously was a unique case where you had pieces of the skull missing. But how much of a structural benefit do you get from getting to custom bend and cut pieces to exactly fit the skull versus putting the same piece on each time?
Yeah, sure. So for sure, if you would get let's say a commercially available bended standardized implant, which doesn't exist like this, but even if you would if you take a flat one and you match it to one type of skull surface, it will, in 99% of the cases, I would say, not fit exactly to the other one. So the skull surfaces are actually quite different. And you really want to get as much of a close fit as you can, because otherwise we have a lot of problems with tissue ingrowth and then also infection getting inside and then basically rejecting this implant.
Mm-hmm. As a kind of related question, the models you were showing me reminded me that I assume that there's some clinically used software for designing custom, say, like plates, let's say a plate for a skull to be as kind of close to this as possible. Were you able to draw from those or take any inspiration from those, or are those just completely different or closed source?
Yeah, so if you're referring to like the general concept, so the general concept
Yes.
are for sure inspired by, like, the titanium implants, for example, are for sure inspired by the human medical parts. But if it's about like the filling up the gaps, like you have this special condition where the skull has a hole and you want to fill up. So in the plastic surgery, there are approaches, but they're actually limited as far as I know, as far as I'm aware, because they are mostly using the mirroring. So that means like you have a hole on the one side, they just mirror the whole skull and then subtract from each other, and then you get the plates. So in our case, for example, the holes were not divided symmetrically, so it would already create a problem. So in that sense, it's a new approach.
Interesting. So do you think that means that this kind of approach could be extended clinically at some point?
I can imagine it can be useful, but however, I'm not sure how many cases you have where this is really like necessary. Like how many cases will you have? I guess it's also a very special case there.
I was thinking partly in terms of kind of like bone structural repair, but also getting into either like implanted DBS things where you need to put something external to the skull, but presumably you'd want to have it as flush and perfect to the skull as possible. Or getting into like more implant territory. that I imagine it would be helpful to actually match it to the skull as is.
Yeah, sure.
All right, we have another question from Melissa French. Thank you, Melissa. What is the age of the animals with these implants / hardware? Have you implanted or have you experimented with implants or hardware in young macaques less than 5 years old? Your work reminds me of the custom head posts offered by Rogue Research. They use animals' recent MRI scans to determine the proper fit.
Yeah, so exactly. So, I mean, we are also using the recent MRI scans and CT scans. And we do not have any, or at least I do not have any experience with macaques younger than 5, because usually, like in our lab, we start, I would say, around 6, 7. Like 7 is more the starting age, like the age for implanting. And then the first question, sorry, was about the...
Yes, the first question was about age. It is a 2-part question. What are the age of the animals that you're implanting?
Yeah, so they were ranging actually from 7 to, as far as I remember, 10. So they were quite young, yes.
Yeah, I think that answers the question. Does anyone else have, any panelists or anyone else have questions?
I've got one. So what kinds of implants are you guys using this for? And is having this like customized implant, is it especially important for some kinds of implants or like certain kinds of methods of recording like versus other methods?
Yeah, so I think there we have different cases. So first of all, the head post, the titanium head post that you use for head stabilization is for sure, like it's one of the standard implants that we have. And that's something you like usually make sure that it fits very well, because I mean, it's titanium and it should fit very well, basically. The other chambers that we, especially with the design that we have, that's what I wanted to say, sorry. So like there are different approaches. You can have also head posts that just have basically an MRI pole, and then you just put cement on it, and then it's kind of adapted to the skull. But with our method that we have with the long legs, you really want to make sure that it fits as flush as possible. Then, of course, then we also have the case of the wireless recordings, which is a super special case in the sense that this type of implant was not existing before. So you have your arrays, you have your array connectors, and you want to really, of course, adapt this very specifically. So for these type of recordings, you for sure need this as well. With the single cell, with the single electrode recordings that I was showing before, just with the round chamber and then the legs, there the legs we put there, but there are also approaches where you can just basically use the cylinder itself and then just put cement around it again. So it's like, depends on which type of implant you're using.
Thank you.
All right, thank you so much, Zurna. Thank you everybody for your wonderful questions. We're now going to move into our final speaker. So now we're going to go from